Hello, in this video we'll be discussing about genetic algorithm, a stochastic search technique that is used to find workable solutions to complex problems. These problems often become tedious when tackled using traditional methods due to a variety of reasons like a large solution space or changing constraints or even conflicting goals. Obviously, we'll start with a simple problem like a 0-1 knapsack problem and build our way up to something more complex like vehicle route optimization. Now, genetic algorithm is called stochastic because of the inherent randomness in its search process. We'll take a closer look at where this randomness comes in and how it is actually useful when we go through the flow of the algorithm in detail. Genetic algorithm is inspired by principles of natural selection and genetics. We start with an initial population of possible solutions. Some of these will perform better than the rest, and those are the ones that will be given advantage when selecting candidates for crossover to create the next generation. In other words, the fitter solutions are more likely to pass on their traits. Such solutions will undergo random mutations as well. By repeating this over and over again, the solutions gradually evolve and we move closer to better solutions to the problem at hand. Now, the key thing to remember here is that genetic algorithm doesn't promise the optimal solution, but they're great at providing a practical one much faster. You'll notice that these have wide applicability. They can be used to optimize neural networks, solve scheduling problems, and many other complex optimization tasks. And this flexibility comes from the fact that genetic algorithm is problem independent. The same approach can be applied to completely different problems. The real challenge, though, is in defining what a solution looks like and how we evaluate its fitness. You see, this problem independence is exactly what makes genetic algorithm part of a broader family of algorithms known as meta-heuristic algorithms. Now, meta-heuristics are general problem-solving strategies. They're not built for one specific problem, but they can be used for solving many different kinds of optimization problems. To understand this better, let's take a step back and talk about searching. We'll also talk about heuristics and then finally meta heuristics. So optimization is just a search problem only. Search through the solution space. Solution space is the pool of all the solutions to our problem. The goal of optimization now is to find the best solution in this pool, or sometimes just a feasible one. There are many ways to search through this space. The simplest approach is obviously an exhaustive search where we try every possible solution. This guarantees that we'll find the best one, but very quickly it will become impossible to do so uh, in case of very large solution spaces. Alternatively, we could try random search where we simply pick random points in the space and check how good they are. But this approach relies heavily on luck, and then in many cases, we might not even find a feasible solution at all. Both of these strategies explore the search space blindly. They don't use any information about the problem itself. So, to make this a little more efficient, we need some sort of guidance, a way to navigate through the solution space in a better way. This is where we use heuristics. They're just simple rules or strategies that guide the search process. Heuristics help us find good solutions faster, though they still don't guarantee the best one. Let's look at a classic optimization problem, the traveling salesman problem, wherein we are provided a list of cities and the distances between each pair of city. The goal here is to find the shortest possible route for a salesman to visit each city exactly once and then return to the starting city. For 5 cities, we will have 12 possible solutions, uh, 60 for 6 cities, and as we reach 10 cities, the solution space will have over 100,000 possible candidates. This is a lot of solutions to check exhaustively. We'll discuss more about the number of possible solutions to a traveling salesman problem and NP heart problems when we try to solve this particular problem with genetic algorithm in coming videos. For now, it is evident that we won't be checking all the 100k solutions. So let's try a quick heuristic here. Let's start with any city and then always go to the closest unvisited city until we visited each one. We could be starting with any of these cities, city 5, 3, 1, or any of these, and what we simply have to do is just visit the nearest unvisited neighbor, and then as we have visited all the cities, just create a route from the last city to the origin one. Now this provides a workable solution in a very fast way, but does not guarantee an optimal one. Let's look at another problem, the 01 knapsack problem. Here we have a set of items, each with a certain weight and value attached to it, and a knapsack that can only carry limited weight. The goal is to select a combination of items to fill the knapsack such that the total value is maximized, and obviously this is constrained on the total amount of weight that can be carried by the knapsack. Now there are different heuristics that we can use here to make quick decisions. One being a maximum value heuristic, where we simply pick the items with the highest value first until the bag is full. Uh, we could also try a maximum value per unit weight heuristic, where we look the value to weight ratio and then select the candidates that have the maximum value for the least amount of weight. The broader point being that heuristics are problem specific rules. They're designed to fit the structure of the problem at hand. The downside here is that these rules don't port from one problem to another. That is where meta heuristics come in. These are general purpose optimization frameworks. They're not built for one specific problem, but can be tailored to solve a wide range of problems. They provide a flexible structure for conducting this search regardless of what the actual problem is. They make use of low level heuristics internally to guide the search process. So instead of creating new rules for every problem, we can rely on the same high level framework, that is meta heuristic algorithms, and simply tailor them to fit our problem. Now let's take a quick look at the terminology associated with genetic algorithm. When tailoring genetic algorithm to our problem, one of the most important steps is deciding how to represent the solutions. That's because we can only begin the search once the algorithm knows what a solution actually looks like, and that's what encoding is. It is how we represent a solution in a form that the algorithm can work with it. The most common method is the binary encoding, where each solution is represented as a string of zeros and ones. This approach is widely used. It's also very intuitive, especially for the problems where we're deciding on the presence or absence of something, like in the 01 knapsack problem or a facility decision problem. It's also convenient when it comes to operations like crossover and mutation. They're pretty easy to perform on binary strings. And even if our problem involves searching the parameter that is a floating point number, we can easily convert that into binary form for representation. We'll discuss about permutation encoding when we work on the traveling salesman problem. It's just representing the solution as the series of all the cities in order that we'd like to visit them, something like this. Let's work through a small example to get a better understanding of these terms. We'll use a Gaussian curve with a bit of noise added to it. Our goal now is to find the value of x such that this function is maximized within the range, say 0 to 100. Now x has to be accurate to 4 decimal places. Now let's look how to represent this range in binary form. Now when it comes to binary conversion, to represent a whole number as large as x, we need n binary bits such that x is at least 2 to the power n minus 1 and at most 2 to the power n. No, actually at most 2 to the power n minus 1. Anyway, so for example, to represent the number 100, we need 7 bits. Since 7 bits can represent up to 127, we'll talk about constraints in the coming video. But for now, let's just focus on maximizing within the range our binary bits can cover. Anyway, this function will have the maxima around this point due to the properties of the Gaussian curve. Now, for the fractional part, we want to be precise to 4 decimal places. That is roughly 0.0001. To figure out how many binary bits we need for that precision, we look for the power of 2 such that 1 divided by 2 to the power n is about the same number. Now if you plug in 13 here, you'll see that the number comes to 0.00012 and 14 gives 0.00006. So 14 bits will give us more than enough precision. Let's go with 14. Now, for the sake of completeness, let's look at an example of conversion from decimal to binary and vice versa. To convert, let's talk about in the integer part. First, in order to convert a number to binary, you simply keep dividing it by 2 and note down the remainder each time, either 0 or 1, until you finally reach 0. The last division where the quotient becomes 0 marks the end of our process, and that last position corresponds to the most significant bit. So we'll be taking the example 23.125. So the integer part here is 23, so we divide 23 by 2, getting the quotient 11, and recording the remainder as 1. Moving forward, dividing the quotient 11 by 2, getting 5, recording the remainder. We do this process until we get 0, and the remainder here becomes the most significant bit. So while recording the actual number, we go from here to here. Now to go the other way, from binary back to decimal, we take each bit and multiply it by 2 raised to the power of its position, and then add them all up starting from 2 raised to the power 0 at the rightmost position and increasing as we move up. So you'll see in here we had the least significant bit as 1. We'll be multiplying it by 2 to the power 0 and moving our way up and just adding it all up, then resulting to 23. Now for the fractional part, we keep multiplying said part by 2, and each time we record the integer part that comes out, which will be either 0 or 1. Then we drop the integer part and repeat with the new fractional remainder until we've got enough bits or the fraction has become 0. And to convert it back from binary to decimal, we just multiply each binary bit by 2 raised to the negative power of the position, starting from 2 raised to power minus 1 and moving forward to minus 2, minus 3 and so on, and just adding them all together. Now in the example we had the fractional part as 0.125, multiplying it by 2, getting 0.25, recording the integer part, multiplying 0.25 by 2, recording again the integer part, multiplying 0.5 by 2, recording the integer part, and the fractional part is finally 0. And this is the binary representation. Now going back, we just multiply these 0, 0 and 1 with 2 raised to the power minus 1, minus 2 and minus 3, and add it all up, getting 0.125 back. And yeah, this is what 23.125 looks like in binary. Moving on to candidate solution. Now once we have finalized on encoding, each encoded solution to a problem is known as a candidate solution or a chromosome. Each candidate represents a possible answer to the problem that we're trying to solve. Now moving on to population. Population is just a collection of candidate solutions. The genetic algorithm starts with a bunch of solutions which evolve over multiple generations, gradually producing better and better answers to the problem. And the initial population is created randomly. And if for this particular problem that we're trying to solve, let's keep the size of the population as 10. Now moving on to fitness function. Another thing that needs to be tailored to our specific problem is how we evaluate each candidate solution. That is where the fitness function comes in. It helps measure the quality of a solution, as in how well it performs given the problem at hand. To put it in simpler terms, the higher the fitness, the better is the solution. Since for this sample problem, we're just trying to maximize the function, so we can just use the value of fx as the fitness function. Moving on to selection. So by this time we know which candidate solution better than the others. Now we need a selection method that gives a higher chance to the fitter solutions to pass on their traits. Roulette wheel selection is one of the most common ways to select individuals for this. Now, for this, imagine all the candidate solutions in a generation arranged on a roulette wheel, where the size of each sector represents the fitness of the solution. So, a highly fit solution gets a larger sector, while a weaker one gets a smaller one. So, in this example here, you'll see that the red solution has a much higher fitness, so it's taking up a much larger sector as compared to say blue or the yellow one. Now to implement this, we can go by normalizing the fitness values, that is dividing each solution's fitness by the total fitness of the population for that particular generation. This will convert the fitness values uh, such that we can interpret them as probabilities. All of these will be summing up to 1. Now this won't change the size of the area that they are occupying on the roulette wheel, uh, but we can determine these resulting values after normalizing as their chance of being selected to pass on their traits to the next generation. The important thing to note is even the weaker solutions still have a chance of being picked. It's just much lower than the fitter ones. Moving on to crossover. In this step, we pick two parents using the selection methodology that we've just discussed, and we combine their parts to create new offsprings. These offsprings will inherit traits from both the parents, and hopefully combining their strengths will result in better solutions. Starting with the single point crossover, here we randomly choose one point along the chromosome and then swap everything after that point between the two parents. So this will give us two offspring solutions. Uh, let's look at this example. We have parent 1 in blue, parent 2 in red. Let's choose this particular point as the crossover point. Uh, so if you look at the first offspring, the first five positions are taken from the first parent in blue, and the remaining bits are from the second parent in red. And looking at the second offspring, you'll see the first five bits are from parent 2, and the remaining 3 from parent 1. So we just swapped the chromosomes for both of these after the crossover point. And amongst other things in the algorithm, this crossover point is also picked completely randomly. Moving on to double point crossover. Uh, the only difference here is that instead of picking one crossover point, we pick 2 points again randomly, and we just swap the section of the chromosome between these 2 points between the two parents. This means the middle segment of each parent is exchanged while the rest stays the same. Uh, like like before, this also produces two offsprings. The double point crossover gives a little more variety than the single point one, and this can sometimes lead to better exploration of the solution space. Looking at the same example, let's pick these 2 points as the crossover points. So we'll just be exchanging the chromosome between these 2 points, between the two parents. So you'll see that 001 and 100, the blue parts remain the same from parent 1. We've just added in the 00 from the second parent, and same goes for the second offspring. Finally, moving on to mutation. Another mutation is used to introduce small random changes into a candidate solution. In the case of binary encoding, it simply means flipping a bit, that is, changing 0 to 1 or 1 to 0. The probability of mutation is very, very low. It is often calculated as 1 divided by the length of the chromosome. So for each bit in the solution, we generate a random number between 0 and 1, and if it's greater than the mutation probability, we flip that bit. This small amount of randomness helps maintain diversity in the population and prevents the algorithm from getting stuck in one region of the search space. Yeah, that's about it for the terminology associated with the algorithm. Now let's just quickly look at the complete flow of the algorithm. So we start by initializing a population of size n. For our sample problem, we'll be keeping n as 10. Next, for a set number of generations, we repeat the following steps, starting with evaluating the fitness of each individual to see how good they are at solving the problem. Then we select parents based on our selection methodology. Then we perform crossover using these parents to produce offsprings. Uh, then these offsprings go through mutation, and finally we build the next generation using these children. And if we want, we can keep a few of the top performers from the previous generation. This is called as elitism. It is used to prevent the best fitness from dropping from one generation to the next. And additionally, we can stop this repetition if the fitness value hasn't improved for a large number of generations, or if we have already reached the desired fitness level, or we can just let it run for the specified number of generations. And finally, we record the best individual from the last generation as our final solution. Yeah, so that's about it for this video. In the next one, we'll start with a rough iteration of our sample problem, and we'll also be looking at the complete solution implemented using Python.